Good. It looks nice. Mm.
You can't see my pointer though, right?
As an answer to the slides on the website, they are going to be available later in the week. Sorry for the delay.
So I didn't give you the slides yet. As I told you, they are...
Yes, it doesn't matter, because the real reason why we didn't even ask you is because we cannot modify the website at the moment until Omer comes back. So we have to wait.
Is he still hiking?
I hope that he's still around.
So the hiking scene in Vancouver is nice?
It is amazing. Yes, it's excellent.
Nice.
But well, I'm no longer in Vancouver, but when I was there, I didn't do too much hiking, to be honest. You need a car.
By the way, where are you based now?
Now I am in Israel, in the Technion.
Oh, nice. In Technion?
Yes.
Oh, so nice. How are you enjoying it?
It's 7. Perhaps we can start with the introduction. So welcome back to Oops. And this is the second lecture of Augusto Teixeira on Quenched Randomization. And today there's going to be some good and bad boxes. Thanks, Augusto.
Thanks again. So let us recap a little bit what we talked about yesterday and move on to the good box, bad box game of today. So I didn't have a slide to recap, so maybe I should talk a little bit. We talked a lot about how to use this renormalization, multiscale renormalization technique to obtain perturbative results on on percolation. So for example, is it true that if P is small enough, you don't actually can percolate? It's impossible to find an infinite path from the origin. So this we proved in the next lecture. Not only this absolute result, but also a quantitative one that bounds the probability that the origin goes to distance n. You can find an open path from the origin to a distance n. We also then adapted the same argument to work for a dependent environment. So we obtained the same under some very mild assumptions on the environment. The two things that happen in well-separated boxes are roughly independent. So today we're gonna continue this quest doing what I'm starting to call quenched randomization. So it's not a crazy idea, it's been around for a while. It's just that some processes in probability have two sources of randomness. So whenever you hear, for example, random walks on random environments, so what is, you already can hear the two words random. So there are two sources of randomness. First, you create an environment that's of course random, and then on top of this, you do some process, for example, random walk. So people study branching random walks or particle systems on random environments. And all these processes, you employ this language of quenched and annealed. What does it mean? It means that you have two laws, right? And the second one depends on the first one. So the random walk has to first see the environment to be even defined. So usually you can try to understand the random walk as we average over the environment. That's what we call the annealed law. Or fix the environment, what's happening to the random walk. That's the quenched law. So we are going to do a lot of this later in this lecture. So we are going to do percolation, but on a random environment. So first, let's, so the outline of the lecture is going to be collinear defect. So we're going to introduce a model that has these two sources of randomness. Then we're going to talk a bit about negative results, things that provedly cannot occur in this model. And then we're going to talk about positive results. using this technique of good box, bad box. And then we're going to talk briefly about what's the purpose of the last lecture. And we have overviewed renormalization in the last lecture through 5 steps. We are going to insist on this notation of 5 steps procedure. It's almost like an internet meme, like solve your problems in 5 steps. So today we're going to act on those steps, but being quite crazy on the scales, which was the first step, and the cascading property, which was the third step. So we're going to make some crazy changes there. And it's good to explore. As I said, this technique is very flexible in exploring how you can change it. Gives you the possibility to prove things for different models. So I want you to be very fearless in changing the vanilla renormalization explained in the first lecture. So this is going to go in that direction. So if you type percolation on Google Images, you're going to get this as one of the first occurrences. And it gives this impression that the model has more parameters than only one, as we displayed in the last lecture. In the last lecture, we said there is P, the probability of an edge being open, which somehow relates to the porosity in this picture. But here you see that there is another axis. And even with the fixed porosity, you can have percolation or non-percolation. Even with high porosity, you could have no percolation. So what's going on here is that, of course, the independence that we assumed over the model is very restrictive, right? So we're going to deal today with dependent models. We also did that yesterday with these balls, this random Poisson soup of balls. But today we're going to be much more aggressive and deal with something that has infinite range dependence. And if you look at the bottom left picture, you see these slabs. Our model is going to be very much inspired by this. So I don't know if it's low contrast, but in the left picture there, you can see a rock that has been built over the centuries through layers, different layers of materials that accumulate on top of each other. And they may have different porosities. So this, of course, I'm no geologist. I have no idea what's going on there, but this is a kind of motivation to the model that we're going to introduce. Our model is going to have inhomogeneities that are going to be built through layers. Instead of doing it horizontally like in the rock picture, you can see in the right picture that we're going to do it vertically. So what is the model precisely? We first fix a sequence of integers, x0 is 0, then x1, x2, x3, and so on are increasing, strictly increasing sequence of integers. And I'm going to tell you how to obtain this sequence soon, but for now, just imagine you know it. You know a sequence of integers x0 to infinity. And on top of each of these integers, we are going to make a line of edges, vertical line of edges. We are dealing with the first quadrant, z2 square, z plus square. And we only add vertical edges on top of these xi's. For horizontal edges, we add all of them. So I don't know if the dotted edges are visible. I think so. So you can see that some edges that were present in the original Z2 lattices are now just dotted, meaning they're not present anymore. So is this graph clear?
Yes.
So we have to now define how we choose these xi's. So this is going to be done again with randomness. So that's why the model has 2 sources of randomness. First, we have some randomness to determine this sliced graph, this stretched lattice. And then we're going to do percolation, which is another layer of randomness on top of it. So the xi's are going to be random, and they're going to be determined by a sum of IID random variables. So you take psi i's as an IID integer valued sequence, and xi is just the sum for j equals, oops, should have chosen different indices. So xn is the sum for I equals 1 to n of psi I. This is actually just a renewal process, right? So if you know renewal processes, these are sums of positive IID random variables. that you lay down as a point process in the line. So this is, I think, natural, and I'm no geologist again, but it's natural to imagine that each of these layers has its law and it's independent from one another. The graph that we are building this way is definitely a subgraph of Z2. So everything that we proved for Z2 also holds for this graph. So if it's impossible to find an infinite path from the origin to infinity in Z2, which is a larger graph, it's definitely impossible to find such path in the harmed graph, right? So there's no point in trying to prove a perturbative result for P small on this damaged graph. What you're going to do instead is to prove something on the other direction. Is it true that if P is large or very close to 1, you can find an infinite path from the origin with positive probability? So this is the main question for today. This can be rephrased as, is PC smaller than 1? So PC was the supremum where the probability was 0. So if it's always 0, PC is going to be 1. But if it's not always 0, if there is some large value of P for which the probability is positive, PC, the supremum, is going to be also smaller than 1. And of course, the question of even whether PC is smaller than 1 or not depends on the distribution of the psi-i's. And our intuition tells that if psi-i's are very heavy-tailed, so they really create these large gaps of absent columns, it should be much harder to find an infinite path because you have to traverse this column where you cannot move vertically. You really have to be lucky and find all the horizontal edges open. So large size are definitely going to harm percolation, and you're going to see this soon. So this is a simulation of the process. Later you can download the slides and play Labyrinth with this. It's fun. You actually, it's not that easy to find the left-right crossing, for example. And it's especially interesting that you have to move up and down a lot. So you can see that there are these damaged columns that have a lot of absent lines, vertical lines. And to cross those, you have to really look, move vertically a lot to find the crossing. So that's my tip to find the left-right crossing and solve the labyrinth. First, look at the large stripes, white stripes. Find the crossing on those, which have to be really flat. And then you just connect them in the regions where everything is easy. So this, I'm telling this as a kind of silly exercise, of course, but it has a lot to do with the proofs. So the proofs are going to exactly follow this strategy. And again, I told you in the beginning of the first lecture that renormalization is a good tool to turn an intuition into a rigorous proof. I hope you're going to leave this class with this feeling as well. So what's the first result, and basically only result on this lattice, on this model before us? This is a result by Bramson, Durrett, and Schoenman that shows that as soon as the psi-i's have exponential tails, so they're not heavy-tailed, then there is a percolation phase. PC is smaller than 1. And this is almost sure for every realization of the xi's. So we're going to be heavily inspired by this result. They didn't state this result as such, but it's something you can clearly extract from their statements. They deal rather with the contact process, but there is a mapping that makes this essentially the same thing. But we are going to be inspired not only in terms of the question being posed, but also the proofs. We make some significant changes to their proof to obtain new results that we're going to state soon, and also to make the proof nicer to read. I think I'll explain later what the difference is, but I think it's also an improvement. There are other results that are similar in taste. They don't deal with exactly with this model, but Hoffman did something very beautiful that deals with both the facts removed from vertical lines and horizontal lines. We're going to talk a lot more about this tomorrow. Castens, Duravicius, and Vares worked on a similar model where the percolation you do on top is oriented, so you cannot backtrack. You have to always move forward and still be able to advance through these traps. There's a nice paper as well by Dominique Copan, Marcelo Hilário, who's here, and Gary Cosma and Vladas, where they studied a near critical version of this. It's not that easy to state, but it's what they call brochette percolation. It's also a very nice paper that works on completely different techniques because of this near critical flavor. So what is the results that we are going to talk about today? So these are two results that complement each other. One is a positive one and the other is a negative one. So we're going to base our results on the tails of the variables psi. So instead of looking at exponential tails, we're going to look at polynomial tails. And as soon as there is an eta bigger than 1, such that the eta moment of psi is finite, then there is a phase transition. There will be a percolative phase. So for example, if xi's have finite variance, then you have a percolation phase. Or even if they don't have infinite variance, but the moment like 1 plus epsilon. On the other hand, if there is an eta is more than 1, for which eta has an infinite, psi has an infinite eta moment, then there is never a percolation phase, unless, of course, p is 1. Then you can always find this infinite path from the origin. But there is no phase transition, so to say. So really, these two results combined give you an idea that the intuition is correct. As soon as the tails of the xi's are too heavy, you cannot find an infinite path, no matter how large p is. But if it has some reasonable moments, then you can find this phase transition. There are several questions left unanswered. For example, can you improve this in terms of quantitative, like making the two results quantitatively closer? Instead of asking like eta moments for eta different than 1, what can you say if the expectation is infinite or if the expectation is finite? So these are all questions that we didn't even insist much on improving. So I think there is a lot to try there, because it's not like we tried our best and we intentionally left the paper as an invitation to continue this type of investigations. So we're going to prove these two results today. And throughout this process, we're going to see so many modifications to the renormalization techniques we talked about yesterday. So here for the negative result, why is it true that an infinite eta moment for eta smaller than 1 makes it impossible for you to find an infinite path? So this is the easy part. It's going to be just this slide. What one does is we consider a rectangle that's going to be very long in the vertical direction. The basis of it is just 0i. So fix an integer I and take the basis to be 0i. And the height is going to be very large. It's 0 exponential of I1 over eta prime with some eta prime between eta and 1. So you can see that the height is more than exponential, the basis. So that means if you're trying to escape through it as a corridor without leaving to the sides, if you're just trying to survive this corridor, it's impossible, right? It's more than exponentially long. You're definitely going to find some region where all the edges are closed and you cannot cross. So crossing it vertically, it's impossible. Now, what about crossing it horizontally? Maybe you can escape by going horizontally. This is also impossible because given the moment condition on the psi, we're going to find between 0 and 1, there'll be a reasonable chance, and we're not going to do estimates here, but it's easy to estimate the probability to find a trap that has width I to the 1 over eta. So it's a polynomially large jump. So there's a psi that is really long, it's polynomially long, and to be able to cross this gap, you have to find psi I many edges that are horizontally open in a row, right? It's just a gap where you cannot move vertically. So you have to find this stream of open edges. And there are so many that you actually need more than exponential of them attempts to find this. So you combine these two, and you finally find that it's impossible to cross. So, of course, this is just for some I. You prove that there is a chance that you don't cross this box, but use Borel-Cantelli with several different boxes, and you conclude that it's impossible to survive. So this is the easy calculation, which of course can be improved upon. We encourage people to attempt. But we're gonna focus today much more on the positive result. Like, is it at all possible to percolate? So to start this, we're gonna rephrase the whole model in this different formulation. So instead of looking at the jump psi and the landing sites x, we're gonna look at it as a random field. So whenever you land and you have a column, we're gonna put a 1 there. And if you jump over a site, you're gonna put a 0. So the ones indicate a column that is present, and the zeros indicate there is an absent column. So this makes the process a random field on Z, for which we know better results. You can see in the picture above that I changed a bit the definition. Before, x0 used to be the first and used to be equal 0 almost surely. And now we are making a small displacement psi from 0 to x0 that has a different distribution of the rest. So this is a very classical transformation you do on renewal processes to make the 0-1 field there stationary. So there exists, as soon as there is a finite moment, finite expectation on psi, there exists this other distribution chi that makes this 0-1 law invariant with respect to the shift. So we're gonna do this because we like invariant things. So we call this field yn, and yn is invariant. So the biggest thing we're gonna use about this field is that it decouples very much like we claimed for the Boolean percolation, the percolation of balls in the last lecture. So if you take an event A that only looks at the y's from 0 to m, and an event B that only looks at this configuration from m plus n onwards, even up to infinity, these two events decouple quite nicely. So as soon as the xi's have this 1 plus epsilon moment finite, the probability of A intersected with B is approximately the product. The difference from this to the product is basically a decaying polynomial in n. And the exponent is exactly the surplus you have over 1 in the moment there, this epsilon that you got extra. So you see that this is very similar to the decoupling inequality I showed you about the Boolean percolation, the percolation of balls. And this condition 12 there is the only thing we use about the fact that xi's, the ones are given by a renewal process. You could have chosen, for example, Boolean percolation, the percolation of balls, to determine the zeros. As soon as you can prove 12, all the other results are gonna hold true. So these are this is a separating interface. So everything you do until 12 is a piece of the argument, and the rest only uses 12. So again, let's recall our 5 steps. So this is going to be similar. We're going to choose scales, define a bad event, show that this bad event cascades, use recursive inequalities to bound those probabilities. No, the lemma is only about the environment. So as soon as you can prove 12 for an environment, Then the percolation you do on top of this, which is going to be IID. So the percolation is IID. Is going to have a percolative phase P for P large. Great. So then we're going to bound the probability of bad events using recursive inequalities. Then we're just going to trigger it so that it starts holding and holds from them. And this is an interesting point. So we're going to use the 5 steps. I don't want to scare you, but we're going to use it twice, right? Because there is an environment, and on top of the environment, there is percolation. So we first do it for the environment. We have a notion of what a bad environment is, so that the bad event is really about whether the environment is good or bad. And after that, we have a notion of good and bad events for the percolation. Like, is this box not being crossed, just like before? That's a bad event. So we're going to use the 5 steps twice. Sorry for that, but this is quenched renormalization. It has to be like this. So first, as always, we choose the scales. So we're going to choose some very large L0 that I have to delay a little bit how we choose it. And we're going to do, just as yesterday, a sequence of scales that grows quite fast. So LK plus 1 is going to be LK to a power that is larger than 1. So it grows very, very fast. We also pave the integers with these intervals, just the same way as we paved the plane with boxes yesterday. Now we are paving the plane, the line with intervals of length LK. So you can see underneath that this is indeed a paving, and also an interval at scale k plus 1 can be covered by intervals at scale k, as you can see in the picture. So it's not only paving, it's a kind of chained paving. Okay, so now I have to define bad events. This is where I told you sometimes it can get tricky. It's not really tricky, but you see, this is something we spend some time doing. We are going to do this definition of bad event by induction. So it's different from before that we just had the picture of a path. That's the bad event. Now it's going to be an inductive definition, which is something very common in renormalization, that everything is inductive. So at scale 0, we call an interval bad if it has no good columns in it. So you can see that the only bad event there is the red one, has 0, 0, 0, 0. All the other ones have at least one good column in it, so it's going to be called good. Okay, so no mystery at scale 0. Scales larger are also not hard. Suppose that we already know how to construct good and bad, like how to label good and bad boxes at the scale k. So how do we define a box to be good or bad at scale k plus 1? So you can see there are some configurations. So for example, the first box at scale k plus 1 is composed solely of good boxes at scale k. So it's, I hope you can see who did those slides is Marcelo, who's colorblind. So if he can see, I think everyone can see the difference between blue and red. So the first interval is just blue, 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 blue. So everything is good. The big box should be good. The second, sorry, I couldn't read on time. Can you repeat?
So at scale k plus 1, you see a block on the scale k as a column.
Yeah, you can forget that this has anything to do with a two-dimensional picture, right? We're just looking at the line. There are zeros and ones. Of course, later, a 1 will mean that we have a column, and a 0 will mean that we don't have a column. But for now, we're just doing a one-dimensional analysis.
Okay. Okay.
So of course, the bad interval is going to be a bad column in the end to cross. It's going to be hard to traverse these bad columns. So the second interval has 2 bad ones and 2 good ones. So definitely it feels like it's bad, but no, it's good. Here is what we define as a bad thing at scale k plus 1. It's exactly when we can find two bad subintervals that are not adjacent. So that's why the second box is considered good, because it's bad, bad. Okay, these are two bads, but they're not adjacent. So, sorry, they are adjacent. They had to be non-adjacent for us to pollute the next scale. So the third box has two bad intervals that are non-adjacent. So the scale k plus 1 is bad. The third one has only a single bad interval, so it's good. And the last one, you see it has three bad intervals. It's good, bad, bad, bad. So the first bad and the last bad, they are non-adjacent. So according to our definition, we were able to find two non-adjacent bad intervals. So the big one is also bad. So you can see that it's a monotone definition, right? The difference between the third and the fifth is that we have one more bad. It couldn't make the thing good all of a sudden. Was that clear?
Can you repeat the definition at scale 0?
So at scale 0, we really look at the zeros and ones for the first and last time. And an interval is called bad if and only if it has only zeros. So if it has only zeros, it's bad. If it has at least one good point, which is going to be a line in the end, this is considered good.
What do you do about the extremes? Is we consider just the left point?
Yeah, the left point is included. The right point is included in the next interval. That's why you see a 1 there, which doesn't make the second interval bad.
Okay.
Sorry, so doesn't make it good.
Okay. So when you go to scale k plus 1, you need to look at scale k and see and do this recursively to decide.
Exactly.
Okay, thank you.
And this, I mean, it's very hard to take a very large interval full of zeros and ones. It's very hard to define to decide if it's good or bad, because you have to do all the induction down to scale 0. So it seems complicated, but actually defining things recursively like this is very good for renormalization, because renormalization is all about how scale k interacts with scale k plus 1. It doesn't look anything further.
There is any intuition why this is a good way to define bad events?
Yeah, there will be soon. Of course, that's not how we did it, right? We didn't write the correct definition and then we found out why it's intuitive. But here we're going to do the other way around. We're going to first define and later we'll see why it's natural. So you remember that before we already had something like either something is, so in the crossing, we proved that if there is no crossing at the large scale, so if there is a crossing at the large scale, there are two crossings in the smaller scale. So we're always looking for two things in the previous scale. But here we want the two things to be non-adjacent because we want them to decouple, right? If they're adjacent, we don't know how dependent they are among each other. But if they are non-adjacent, there was some space in between to mix. That's more or less the intuition.
I see, makes sense, thanks.
Okay. Okay, so after having defined the bad event, what we prove is that the probability pk, that an interval is bad, decays with k. So there is some exponent alpha such that the probability is polynomially small in the length of the interval. So this is going to be done by first step C, which is this cascading property, but the cascading property is obvious, right? We define the thing in an inductive way, so you don't have to prove the cascading property. You already know that if something happens in scale k, it's because it happened in scale k minus 1. So what we have to do is this calculation that always looks scary, but it's always smooth to carry on. So imagine that we have proved pk smaller than lk to the minus alpha for some k. How can we prove it to the next in the next scale? As I told you, you write pk plus 1 over what you want it to be smaller than, and you want to show this smaller than 1. right? So first we use the cascading property to write it. So if pk happens, then there are two boxes that are non-adjacent, and if the event k plus 1 happens, then there are two boxes at scale k that are non-adjacent and that are bad as well. Let's call these two boxes M1 and M2, right? So how many ways can you choose those boxes? It's the ratio between scales, Lk plus 1 over Lk, square because you're choosing two scales. And after having fixed the two intervals, you have the probability of the intersection. I'm putting the supremum there just to take the worst possible case. But the probability of the intersection of the events is by the decoupling inequality that we proved before. Probability of A inter B is bounded by the product of the two probabilities plus an error. So it's really pk squared plus lk to the minus epsilon. A gamma is the relation between scales. So let's go back a little bit. You can see that we chose the scales lk plus 1 to be approximately lk to the gamma. It's a number bigger than 1. So back to the calculation. So now we have the pk squared plus lk to the minus epsilon. This is the approximate independence of faraway boxes. The left-hand side we rearranged, like it's everything written as in terms of lk, and it's a fight between exponents in the end. You can see there we're trying to do something quite sharp, so we have to really pick the exponents correctly. But if you choose 2 alpha to be smaller than epsilon and 2 minus gamma to be bigger than 2 gamma minus 1 over alpha, and it's possible to do this, that thing is decaying with k. So I'm not going to go into the details of why you can choose these exponents, just trust me. There is a choice of exponents that is quite sharp, like you really have to be precise. As the moments of psi get very close to 1, it's harder and harder to pick this thing, but you can pick it. And now the right-hand side is going to 0. So for k larger than k0, this is smaller or equal to 1. So that's the trick I was insisting on before. Questions? Yeah, that's what I didn't mention. I was delaying, but not delaying, I was avoiding a little bit. So let's do another exercise. Let's imagine that we have a very large moment of the variables psi. So epsilon is really large. Then we pick 2 alpha to be close to epsilon. And then that means alpha is large. You can see that in the second equation, the denominator is large. And the numerator, you can make gamma as close to 1 as you want. So the numerator is also small, and the left-hand side is basically 2. Right, so I'm not saying that you fix gamma and now choose alpha. You have to choose alpha and gamma at the same time. Gamma is going to be ridiculously close to 1, so that the right-hand side of the second inequality is very small. Yeah, now, so I was playing with epsilon large, but now you can really think. Take any epsilon, choose 2 alpha is smaller than epsilon, and now choose gamma ridiculously close to 1, and both inequalities are going to hold. Is it clear? In renormalization, oftentimes it feels like you're cheating because you're choosing the constants after, and it seems like it's a cycle. Yeah, epsilon is the decoupling of the environment. It's the moment of the size. It's never, in the paper we make sure that we don't give the impression that we are cheating because we choose all these constants in the very beginning. And then you verify, of course, it's possible to pick these constants. Now let's do everything so that it doesn't feel like we are choosing something after in a cyclic way. But it's very boring to start a discussion like pick alpha smaller than epsilon over 2 and gamma such that. But in the paper we do it. So how do we trigger this? Remember that we delayed choosing L0, the first scale. So now we choose L0 to be very, very large, so that the probability to find a bad box in the beginning is very small, because remember, at scale 0, a bad box is a box that has no ones inside. Right? So if L0 is large, it's very hard to find a box full of zeros. Of course, this is actually tricky because when we change L0, remember that L1 is a function of L0, so we're changing all the scales in a way that it's messy. So this is actually some calculation that I'm hiding, but it's possible to do. We choose L0, alpha, and gamma at the same time, and K0, and everything works. So the conclusion is that the probability, up to now there's no percolation. It's just proving that typical boxes are good in that definition of good. So that's what they proved. They proved that the probability of bad is going to 0. So typically we are going to see good boxes around. And what we're going to do now is to do percolation on top of this and show that typically you can cross those good boxes. So you're going to find the percolation phase. So as I promised.
Augusto.
Yep.
Sorry. So we showed that pk goes to 0.
Yeah.
So it means that the probability of finding a bad box at scale k is going to 0, right? Or
yeah.
Okay.
Exactly.
Thank you.
And now we're going to show that we percolate very likely on good boxes. So as I promised, we're going to do steps A to E again, all over. So first choose the scales, and that's how we're going to really get crazy. I told you that we have a lot of flexibility in choosing scales. So we chose already the scales for horizontal line. We're going to keep those fixed. These are the LKs we always used. But vertically, we didn't choose those yet. And we're going to choose them as H0 equals 100. Easy there. And the next scale is going to be the previous scale times an exponential of LK plus 1. To a power mu that is between 1 over nu and 1. So I know it's a complicated, it's a strange definition of scales, but let's get an intuition about this. Essentially what we are saying is we know by the first argument, right? Remember the negative part of the argument saying there is no percolation because there are these barriers that take a lot of attempts to cross. This height is exactly the height you need to cross the typical heavy barrier. So you see, it's actually intuitive. You choose the height to be such that you have a chance to cross by just brute forcing, trying to find a horizontal large stretch crossing the worst barriers you find. So this is going to be our choice of vertical scales. And now we define two crossing events, the CM and the DM. So for a box M, we're going to take these two things. It's an L shape. So the C is the horizontal crossing, the D is the vertical crossing. And we want to show that the probability of those go to 1 using renormalization. Okay, so RK is going to be the probability that C doesn't happen, and SK is the probability that D doesn't happen. Okay, and they are a supremum over the whole environment. I think you cannot see there, but it's a supremum over all the environments for which the basis is good. So you take the worst possible environment, but constrained to the fact that the box is good in the basis. And now look at the probability. You can see that for D, it's a single interval because the vertical crossing only has one interval in the basis. And for C, it has two intervals. Okay. So now let's try to estimate RK and SK by induction. So we're going to show that both RK and SK decay very fast with K. So this is the final aim we have, the decays of the R and S. And the way we do this is one at a time. So we're going to show that if the maximum is small at scale K, then R is small at scale K plus 1. And in a second lemma, we show that if the maximum is small at scale K plus 1, sorry, at scale K, then S K plus 1 is also small. And now we have the induction. So why are we splitting like this? Because it's really a different strategy. To cross horizontally, you have to cross those barriers. But to cross vertically, no, you just choose a nice region and you go. So it's a very different strategy. And again, it's translating the intuition that you build before even starting the proof. So let's dig into the proof and see if we can find the intuition appealing as well. So remember, we have steps from A to E, right? We already did step A, which is defining the weird scales. The step B, which is defining the events. The bad events are no crossing horizontally or no crossing vertically. We have two bad events, actually. And now we're going to do steps D and E for each of the events in separate. So first you're going to do the R, the cascading property for the C event. So remember, these boxes are very elongated, right? The vertical scales are gigantic. If you want to cross it like this, it's very intuitive to try to cross in several lines at a time. So you have several attempts. So if we cannot cross the box at scale K plus 1, it means that in each of these corridors, you could not cross, right? So all your attempts failed. And if a crossing in a corridor failed, it's because you didn't have the picture underneath. Because if you had the picture underneath that all these C crossings and D crossings happened at the same time, you could stitch them together and find and traverse the corridor. So this is the cascading property, relating C with both C and D at the previous scale. You see what I mean? So if there was one corridor for which all the events C and D like this have happened, then you would have crossed. So not crossing means all corridors have at least one failure event in the previous scale. So this is quite different from what we did before. Like before, it's like if there's no event in the, if the bad event happens in the large scale, it happens twice in the previous scale. Here you're saying if it doesn't happen in the large scale, it happens in every column, and there are many of them. So in every row, and there are many of them. Right? So this cascading property implies something for the probabilities. Is there any question? So if we estimate RK over what we expect it to be smaller than, we use the cascading property. So now you can see that we have a big parenthesis to a power that is, this power is the number of corridors we have. So we failed in all the corridors. Now let's look inside the parenthesis should be what it means to fail in a corridor or bound to this. So if you failed in a corridor, it means that 1 minus you succeeded in a corridor. Succeeding in a corridor is, as I said, if all the events C and D happen, you do succeed. So we have here a bound that says, yeah, if all the events C and D happen in the previous scale, you do succeed in the corridor. So 1 minus this is a bound on how you fail in a corridor. Now we plug the bounds we have for RK and SK. And I'm not going to do it in detail, but essentially you see, let me just convince you that the very basic union bound gives you the result. You already have an exponentially large probability, is great. An exponentially close to 1 probability that you cross in the previous scale. So asking all those to cross is very cheap to pay, right? There are polynomially many of them. You ask for all of them to cross and it happens. So every corridor is already very likely. So when you take 1 minus something very likely, this is very small, and you still take it to an exponential power, so this becomes ridiculously, ridiculously small. There's no chance. So this is smaller than 1 for large K. But that felt too easy. I mean, we already had a very high probability of crossing. We cross a corridor very easily, and then we still have many attempts. So what's going on? Why is it so easy? The reason is was cheating a little bit. So sorry for that. We have to go back and see where I cheated. Remember that RK is the probability that you do cross, but when things are good. And things cannot always be good, right? So let's revisit the events, the cascading property of the event, see? So again, if we cross horizontally, so if you don't cross horizontally means we failed all the corridors. That's true. But now in those corridors, there are good boxes where we can use the estimates on RK and SK. But there are some bad boxes marked in red here, right? So for those bad intervals, we cannot use the bounds we have on RK and SK. What you're going to do is you're going to make a straight line, request all the edges to be open, and just pierce through the defect box linearly. It's going to be very costly. But as I said, we were in very good shape before, so maybe you can pay this costly price. So now we redo the calculations, and you see that the probability to fail in a corridor is essentially the probability to fail in this piercing attempt, because the rest is very cheap. Paying for the crossings in the good regions, you pay 1/2 and that's it. It's paid for. Now,
can I ask you a question? Sorry.
Sure.
These bad boxes, you only have one because otherwise everything would be bad, or you cannot have
so
two.
You can have
the
two
same.
if they're adjacent, like in this picture, in the end of the picture.
Oh, okay.
But you cannot have 3, for example. So that's why we do these piercings that have length 4.
So it's costly, but you have some control on how much it costs.
Yeah. And the cost is exactly written there. It's 2 to the minus 4 LK. I'm writing 8 because there are 2 places where you have to do this. And I'm writing -1 because this -1 just to pay for the good things to happen. Like when the boxes are good, you almost don't have to pay. And then you do your math. This is more than 1. We're done. So now it's really a proper proof.
Augusto,
yes.
Now that it's important they control on the environment, right?
Exactly. This is exactly what we are using about the environment. Everything we know is that we're trying to cross a big, good box. And a big, good box, at worst, has 2 smaller adjacent bad boxes inside. So you just take that situation. Yep.
What about the PK that you showed that goes to 0? How it appears in this calculation?
It doesn't. So that's the interface between the 2 renormalizations. First, we proved that a typical box is good. That was using the first renormalization. Now we can take the worst possible environment as soon as it's good and do the percolation.
I see.
So you don't have 2 sources of randomness in the second renormalization. Just fix an environment that is good and you're going to cross it.
I see. Thanks.
Can you come back to this 3 constant, alpha, gamma, and epsilon? If you have fixed gamma and epsilon, why you can choose alpha?
So in the environment, you mean?
Yes, yes.
So we didn't fix gamma. So what we actually do is the following.
two inequalities. Why you can satisfy these two inequalities? Two.
Yes. So what we do is epsilon is given, right? And maybe very small. This is the only thing that is given. Then the first thing we do, we don't pick gamma just yet. The first thing we pick is alpha. So we can pick alpha to be epsilon over 3. That's going to work. Now that alpha is chosen, we pick gamma bigger than 1, but extremely close to 1. Now the second inequality is going to hold because the left-hand side is bigger than a half, and the right-hand side can be made as close to 0 as we want.
Thank you. Thank you.
Welcome. So this is, as I said, this is why in the article we first choose all the constants to not give the impression that we are choosing them in a cyclic way, and then we do the construction. Because if we do the construction, it gives this feeling that we already chose gamma. So how are we choosing gamma again now? Re-choosing gamma. So yeah, it's always an important point in renormalization to pick the constants beforehand. So here, I'm not going to do this calculation in detail, but I'm just going to show why it works. So you see that the price we pay to cross is 2 to the minus LK. It's really piercing an LK box, or 8 LK, doesn't matter. But now the number of attempts you have is bigger than that. It's LK plus 1 to the gamma. This is the number of corridors. And LK plus 1 is LK to the gamma, and gamma times mu is bigger than 1. So you have something bigger in the number of attempts. So you see that the intuition is really coming there. Like the number of attempts you had to cross is much bigger than the difficulty to cross it. So there you have it. And now we have to do the D calculation, right? We just proved that RK is small. Why is it true that S is also small? So it's a completely different setup, because you remember we may have these bad intervals, but we completely avoid them. So we can have a bad interval, but either the left third of the box or the right third of the box don't have them. So we try to survive in a region that there are no bad intervals, and we have to go up. So how do we do this? So just as before, you see that in this picture here, if we have several crossings, C and D, tiled together like this, we make a corridor crossing. So they kind of stitch together very nicely. Here we also use the same. If we have several crossings like this, they stitch together very nicely. So we consider this as what we sometimes call a renormalized lattice. So every box in the previous scale is a site now, and we say that if it's open if there are these two crossings, horizontal and vertical. And if you find a path of open sites, renormalized sites, it means that you have an open path of regions where you can cross like this, and you can stitch those crossings together and find a real crossing. That's what you're looking for. So essentially, by choosing the events that cross kind of in the hard direction, they cross a long rectangle like this, you make sure that crossings of good boxes, like paths of good boxes, translate into paths in the microscopic picture, like really back down there to the edges of the lattice. So this is a very common argument. It's essentially saying, you know, we were trying to find a path before, we're trying to find a path now. So renormalization is often about translating something that you had in the original model into something about renormalized sites. So I don't have much time left, so I'm not going to do this in detail, but if you don't have this crossing from bottom to top, remember this is a very long box to cross, so it's going to be very hard to find this crossing. But if you don't find it, it's because you have not only two, but several boxes that didn't work out. right? You have to have a blocking surface where the good event didn't happen. So we do a kind of counting paths argument. I bad-mouthed counting paths a lot yesterday, but today we're going to use counting paths. So we just drop every odd of them to get those paths disjoint. Sorry, not disjoint, separated so that they become independent, because nearest boxes, they have a dependence through the paths, right? The paths are long and one enters the other box. So it just takes a subset of them to make this independent. And again, it's just a calculation. Sk over what it has to be smaller than is bounded by the sum over all the paths that can block you. For every path, you count the number of them. This is 8 to the n. You pay the price of the path being open. It's exponential. It's like the probability that you estimated in the previous scale to the length of the path. You also have to choose the starting point of the path in the left wall. And it's just calculations. It works. And why does it work? Because you choose, again, a vertical growth that is big enough for you to allow to cross the barriers, but not too long that would make a barrier to the vertical crossing. So here is where you have an upper limit to the growth of the vertical scales. You can really see those by the choices of beta and gamma there, but I don't have time for this. But that's it. So I think I went too much into the details of the proof. I hope it was not too exhaustive. Probably it was. Sorry for that. Just the moral of the story is that we managed to make this distinction between first the environment, then the percolation, and we used this good box, bad box idea, which was very efficient because we had these big defects that, big jumps of the psi. They're big defects. And when we declared the box bad, we actually said, okay, this is the worst possible thing. Let's just cross it horizontally. We have no notion of something between good and bad here. And this is very good for this model. It's fine. But this uses a lot of vertical space, because as soon as you find some boxes bad, you have to really go up a lot to find the crossing. So in the next lecture, we're going to have a situation where we really have to measure how bad the box is. So this is going to be the last ingredient of renormalization I want to introduce. Like, can we call a bad like 0 bad or 1 bad, 2 bad? Like give it a number of badness. And it's going to be easier to cross a 3 bad box than a 5 bad box. So this is what awaits us. Thank you very much again. So for the picture of today, I chose my favorite fruit in the universe here from my region, and maple syrup, which is what bees are trying to imitate for millennia. Thank you.
Thank you. So let's thank Augusto. Before we pass to